Okay, thank you. So I can start. So as Tony said, I'm going to update you on the OASIS3-MCT coupler. Some of the developments that I will show here were realized even a couple of years ago, but I still take the opportunity to present them here as they were not presented at the previous workshop. I would like to thank my co-authors, so Laure Coquart, Tony, Gabrielle Jonville, Eric Maisonnave, and Andrea Piacentini, for the hard work done on OASIS3-MCT and for supporting myself. Next slide, please. So I'm going to give a historical overview and then an overview of the user community, and then simply describe the latest developments and the ongoing developments and give some conclusion. So OASIS started in 1991, as you probably know, and we had the series of OASIS 1, OASIS 2, OASIS 3, which was a sequential coupler. And then when the PRISM project started, we started thinking about parallelism in the coupler. We started developing OASIS 4, which was used for few coupling. But at one point, we decided not to go on with the development of OASIS 4. And that's when we put MCT, so the model coupling toolkit, developed at Argonne. So we put this under the hood in OASIS 3. Actually, that was work done by Tony. And that's how we produced the first version of OASIS3-MCT. Now, the last version of OASIS3-MCT is the 4th version, and it's been released in June 2018. So regarding the community, we did a survey in last year, and we really bugged all the people who download the sources to ask them if they were really using the software. And the result was quite pleasant, because now we are sure that at least 67 climate modeling groups around the world use OASIS3-MCT to assemble more than 80 coupled applications. OASIS3-MCT is used in 5 of the 7 European ESMs participating to CMIP 6. So this is the list of the latest development that are included in OASIS3-MCT 4.0. The ones that are in bolded, I will go in more detail. I will present them in more detail just afterwards. So we now support bundle fields. We have the activation of the no interp option, which I will describe in more detail. We have new and more performant algorithm for the global conservation operation. We upgrade to the 2.10 beta 1 MCT library, which reduces the cost of the initialization of the MCT routine by order of 10 or 100. We did some debugging of the coupling initialization, which has a big impact. We did some optimization of the communication, and we now have a hybrid MPI OpenMP parallel version of the script library. And then since the release of OASIS3-MCT 4.0, we have additional developments which are available, let's say, in the trunk version, which is not officially available, but if you are really interested, you can ask for. So now we have fractional mask for the global conservation operation. We have new options in the global conservation operation to conserve fields which are a bit tricky because they have an average close to 0. We have the normalization by the true area of the mesh. That is the area of the mesh as considered by the models themselves and not necessarily as calculated by the regridding library. And there are different bug fix and details that I will not go over now. So this is a slide on the no interp option, and this has a strong impact on the tests we did with the easiness benchmarks, which results were presented at the previous workshop. You see here in green, that was the results before for OASIS3-MCT. And in fact, even when we had, I mean, this benchmark is based on a test where we couple two toy models which have the same grid and the same decomposition, which means that the regridding basically does not do anything, but we were still forcing the multiplication by a matrix with the identity matrix, which is pretty useless, but it was kind of a, you know, just the matrix that represents this perfect mapping. And so basically we removed that. We allowed the option not to use any matrix vector multiplication. And now you see the results. This is the light blue curve. And you see that there's a perfect scaling, which is pretty good, up to 10,000 cores. And basically, this is the scaling of the MCT library itself. So we were really pleased with those results. Yeah. This is a slide that gives you some details on the new algorithm for the global conservation. I will not go into all details, but basically the bottom line is that now we have the what we call the reprosum option, which is now the default, and it's a algorithm which is, let's say, bit for bit reproducible, except in extremely rare cases that we have never seen in practice. And it's much faster than the original bit for bit reproducible core scheme. So that's usually what we recommend now to use for to have a faster operation and a bit for bit reproducible one. So here is yeah, that's the we debugged the initialization phase. It was pretty surprising for us, but when you in operational mode, when you were using a level of debug information in the log file, even if there was very few information, as all processes were writing to the same file, this caused a strong bottleneck. And we had problem at, I mean, with Météo France and with our model, we were seeing that the initialization was starting to be quite costly. And this was the cause of the problem. So now you see that those graphs shows you the time for initialization with respect to the number of core per components. And you can see that for a realistic case, which is the NEMO 1/4 of a degree, coupled to the Gaussian reduced grid T799, we now have a reduction in the initialization time of 82%. For the more theoretical case of the easiness benchmark, with the same grid on both sides but opposite decomposition, we have a reduction in the initialization time of 99%. So this was a very good improvement of the initialization phase. Now we also did some work on the optimization of the communication using the mapping weights. What you have to understand is that the current implementation in OASIS3-MCT, when you do some regridding and communication between a source grid and a target grid, it requires to map the target decomposition on the source processes. And then the data is sent to that decomposition, and then it's sent afterwards to the target processes. And before, we were doing this this mapping of the target decomposition on the source processing was done. That's what we call the decomp 1 day option. And then with this option, each target grid point was assigned to a source process in a in a trivial 1D way. And now what we do, I mean, the algorithm is a little bit more intelligent in the sense that a target point will be will be mapped to the process which holds most of the source points that is needed for that target point. And so when we do this, the cost of the mapping communication is greatly reduced in numbers of and the size of messages. Of course, the cost for the sparse matrix multiplier is the same, and the cost for really the sending the data from the source and the target is the same. But just because of the improvement of the mapping, the first phase, then we get pretty much improved performance. So this is an example of what we get. On the left, this is the time for a ping pong exchange. This is still the easiness benchmark case with two grids of 9 million points on each side. but having an opposite decomposition. And you see in blue, this is the time for the ping-pong exchange with respect to the number of components, and in orange with the previous scheme, and in orange that's what we get now with the new the new algorithm using the mapping weights. And you see that for that case there's a reduction of 75%, which is pretty good. This is a more realistic case with, again, the NEMO a quarter of a degree grid coupled to the Gaussian reduced grid T799. And you see that in this case, at 10,240 cores, we have a reduction in the total time for the ping-pong exchange of 24%. So we were also very happy about this improvement. Finally, what I want to describe it in a little bit more detail is the parallelization of the script library. We perform a hybrid MPI OpenMP library, and you have here two graphs, which gives you the time needed to calculate the remapping, the regridding weights as a function of the number of OpenMP tasks. And you see that all for different algorithms, and you see that all algorithms scale pretty well. So on the left, it's for the quarter of the degree to the T359. And on the right, you have the ORCA grid, the 12th of the degree to the T799. So you see that there's at high number of core, you can reduce the time needed for the calculation of the weights by order of 10 or 100, which is pretty good, and what was becoming essential because with the grids we have now, the use of the sequential script library was not possible anymore. So regarding the ongoing developments, we have a beta version of an API for Python code. This is developed by STFC in the framework of the ENES project. We are working on additional and improved diagnostics and pre and post-processing transformation. We are redesigning the Lucia tool, which is used for load balancing in collaboration with BSC in Barcelona. And the big task we are also working on is the analysis of different library, a different interpolation library to replace basically the script library. This should be done in the next version of OASIS, which is planned for December 2021. And we are also thinking about supporting grids with mask evolving with time. So I will not go over all the details, but this is just a result. I mean, before analyzing other libraries, other interpolation libraries, we made a very deep analysis of the results of the script library. And we did this for different types of grid, for the different normalization option, using or not the Lambert equivalent azimuthal projection, which is available at the north to avoid the distortion of the cells near the pole, which is shown on here on the graph at the right. And all the results of this detailed analysis is available in two Surfax technical reports. So if you are interested, please just contact me and I can send you those reports. They are available on Surfax website. And basically the result is that everything is okay with the script library for regular lat-long grid and logically rectangular grid and icosahedral grid. But we still do have problem for the Gaussian reduced grid. The Gaussian reduced grid is, it has a certain number of cells, and then when you go up to the north, you have a reduced number of cells per latitude row. And basically what we were doing before is that each cell is defined with 4 vertices. But you see on the graph on the left that if you define the mesh, the cells like that, the corner of a cell are not necessarily the corner of a neighbor cell. So this is, let's say, it's not really well defined. So what happens when you define the cells like that is that if you project in the Lambert space, the cells, which are represented here in red, I mean, the border of the cells will not match, and basically the grids will not completely cover the whole globe. There will be holes in your grid, and of course this will give bad results for the regridding. So basically what we did, we redefined the cells using for each cell, we were using the 4 original corners, but also the corners of the neighbor cell on the lower and upper latitude row. And with doing this, some cells have up to 7 vertices. And we were hoping that so now the grid is really well defined and everything is connected. And we were hoping that this would solve the problem, but we still have a significant error with and without the Lambert projection for the dest area option. So basically, we are working on the analysis of other library. ESMF is for now a very good candidate, complete, efficient, and very good user support. We still have some issues regarding the North Pole with the ORCA grid, and I have to send an example to Bob about this. We looked at the Atlas library from ECMWF. It's a very appealing library, but we cannot use it on the short term because there are still different things missing. XIOS has a very interesting second order conservative regridding. We have here an example. So on the left, you have an analytical field on the quarter of the ORCA grid. At the center, this is expressed on the 2-degree regular lat long grid. And on the right, it's regridded on the ORCA grid again. And you see that the second order conservative recreates a good gradient of the fields. So the conclusion, OASIS is still there and lively. We have a large and growing community. We have active development and we are providing active user support. We need to reshape the interpolation library. This is a target. This is our objective for the next version. And our next challenges will be, I think, internally about the use of MCT. Will this be good enough for the next big coupled system and the support of dynamic grids?